Recording is in progress. Okay, good evening, everybody. I think we should wait a few more moments to start this webinar, which has been organized by the Mersey and West Cheshire Local Network. We just try to see how numbers go up. I think we have to give it a minute or two. I think it's coming up. It's increasing nicely. It's 1 minute past. A few more seconds. I'm after your patience. Thank you. I think it's about the right numbers, but I believe it will still be increasing. But I think 2 minutes past 6 o'clock, I think it's time to start. Let me tell you, it's a pleasure for me to welcome you on this webinar organized by the Mersey and Western Cheshire Local Network, joined by 2 groups, manufacturing and management, and the biomedical engineering group. Today's webinar will be about optical 3D metrology and advanced healthcare applications. First, I'd like to give you a little intro, a short intro about the network and the work, what we do and how we do it. That's it. Right, so we aim as a local network, and of course these 2 groups, we aim to share engineering success and innovation, and to take engineering as a very wide area, and raise awareness of the importance of design, manufacturing, management, and integration, and promote novel technologies, techniques, and best practices in the region. And of course, that's what we are going to do today. How do we work? Well, the structure of the local network, we have a steering committee, we call it Local Network Committee, and we have 6 groups. 2 groups are perhaps the most important ones, dealing with young people, school liaison officers. It's about schools and colleges and young professionals, which covers 18, 30 years old. And then the 4 technical groups, biomedical engineering, electronics and e-systems, energy and environment, and manufacturing and management. The yellow or orange color is the one which highlights the 2 groups involved today, in biomedical engineering and manufacturing and management. The biomedical is quite new. Activities, the main activities of the network, basically it's based around events, which comprise technical visits to companies, presentations, seminars, and we do recognition events every other year. We do an annual dinner, we do events newsletter twice a year, and we provide student excellence awards. Obviously, we all of us experienced this COVID thing, which was a big obstacle in our work and our life, and we started to go back to normal, and perhaps from September we'll be back in full normal mode. You are here today, and I'd like to ask you to contribute to our works. As you have done today, nicely come to the events. Please do join a group if you wish, and please involve your company. That's the right time to do that, because we are just about to plan our events for 2023. I'd like to ask you to contribute in some ways. Please do contact us. My name is Andrew Cardos. I'm the first one here. well, this is not in any order of importance. I'm the Group Chair. Michael is the Deputy Chair, and we have the Biomedical Engineering. They have 2 co-chairs, Shruti and Jack, and we have the boss, Godfrey Evans, who is the local network chair. Today's event, as I just mentioned at the beginning, it's about optical 3D metrology in advanced healthcare applications. Organized jointly with GOM UK Limited, which is a Zeiss company these days. Speakers today, Stuart Dix, GOM, who is a GOM technical and commercial engineer. Amy couldn't make it today. She has other things to do. So today's speaker will be Stuart. A bit of housekeeping. Webinar arrangement, it's about 35-40 minutes. It's a nice round presentation to be followed by a QA session. Please use the question box to raise your questions. Now, I put it in blue. Please note this webinar is being recorded. It will be available to you. That's great. And Stuart has kindly promised to let us have his presentation in a PDF form. If anybody wants to have it, please contact me. We provide CPD continuing professional development certificates on request by myself or Michael. But IT staff, Sandra has kindly copied it into the chat box, so you can download yours directly. But if you can't manage that, I'm here. We are here to help you with that. A bit of near future forthcoming events. I like to promote that. It's I think it will be a fantastic fun, a graduate apprentice seminar about digital technologies enabling business reimagination. It's in cooperation with STFC Dasbury and VEC, that's Virtual Engineering Center, University of Liverpool, on the 15th of June, 2022. It would be great to see you there. I think that's it now, and I'll stop sharing the screen, and I'll have to ask Stuart to take the floor. If it was a physical event, take the floor. Take the screen, please, Stuart.
No problem.
Could we have your stories, please? Thank you so much.
No problem. Yeah, firstly, thank you, Andrew. Thank you for the invite, firstly, and the welcome. Hello to everyone for joining this evening, and for sparing an hour or so of your time. So I'll jump straight into sharing my presentation. So what I will do is I'll just stop my video because it will probably help with bandwidth and things to run smoothly. So what we should have is the start of the presentation. So welcome everyone. My name's Stuart Dix. I look after sales of GOM equipment in the UK, specifically in the Midlands or the middle of the UK. And ordinarily I would have been joined by my colleague Amy Hatte, who specialises in one of our portfolios, the testing equipment. She can't be with us today, so I'm going to do the testing bit as well. But any questions at all, please throw them into the question box or the chat box, and we'll try and come to them at the end. So what are we going to look at today? So a little bit of information about who GOM are, who Zeiss are, and where that link comes in. What solutions we actually offer to the industry. So what does our equipment actually do? And then we're going to look at a couple of case studies. One of them is looking at actual medical fitting of a knee using one of our pieces of equipment, Atos system. We'll also look at Aramis. I'll talk a little bit more about what the two systems do and how they differ. And then we've got a little bit of information at the end just for a bit of fun, and then we'll summarize and as I say, go into Q&A at the end. So the company itself, GOM, it's based in Braunschweig in Germany. The next slide is going to lead on to the sort of development of the company and who we are in today and over the next few months. But the company, as I say, was founded in 1990, privately owned company. And in the UK, we're based in Coventry, and we have 20+ people there, dedicated to sales, support, marketing, training, aftermarket care. So basically everything. So when a customer buys a system, it's a complete journey to get them on the road and gathering good data. So for the last 3 or so years, we've started to merge closer with the Zeiss group. So we're now part of Zeiss. And if many of you out there don't know who Zeiss are, they're quite a major player in the manufacturing and also metrology world. And a lot of people wear glasses, and the actual lenses themselves are quite commonly Zeiss lenses. They also produce high-end optics for digital SLR cameras, microscopes, and those sort of things. There also is an industrial quality section, which is highlighted here, and this is where GOM fit in. So very much the industrial metrology and inspection of industrial components. So because of this joint relationship now, this joint venture between GOM and Zeiss, we now have quite a wide portfolio, from 3D metrology to actually measure the surface of a component, the exterior. We also have 3D testing, looking at real-time deformation, displacement, how things move. We then move on to industrial CT or X-ray systems. So this is where we can actually penetrate the material of a component and look internally as well as externally. So we can look at dimensional information inside as well as looking for defects. We also have contact systems, CMMs for contact measurement, non-contact vision systems with multi-sensor, and we also have handheld or tracked laser scanning systems. So quite a wide range of systems to pretty much suit any application, any budget, any need. So specifically the GOM equipment that we're going to talk around today is specifically Atos that we see on the bottom left here, and then also Aramis on the bottom right. These are the sensors, the actual hardware that we develop, and this is developed at the facility you saw in Germany. And we also develop and produce and sell our own software. And this is a widely used software. I'm not sure if many of you out there are manufacturing components, producing, or have any need for inspection. If you do, there's a reasonable chance you may be using our software in there somewhere. And to finish it all off, we also have completely automated solutions you see here. So this is where our sensors are mounted onto the end of a robot, and it's a very much a high accuracy, high repeatability method of inspection. And just one final thing on the software. As I mentioned before, it's our own software, we develop it, and all of our solutions come with a seat of software included. And the link that you just seen pop up on the screen here, this allows you to download a free version of the software. So if you get a chance, and if you want access to this link, just pop a message in the chat and I can get back to you with some more details. But this not only allows you to look at CAD data, you can start to use maybe information from a CMM or from a scanning arm, and you can pull that data into our software. So it's very, very powerful. And as I say, free to download. And then as you grow and you need to do more with it, there are further options that you can do. So a little bit of information about Atos. I mentioned Atos before. What is Atos? So Atos is the actual hardware for capturing 3D data. So it uses high-speed fringe projections to essentially map out the surface geometries of the part. We're capturing hundreds of thousands, if not millions of data points, and we're creating a 3D digital twin of the part. And once we have that exact copy of the real part in front of us, we can then start to inspect and compare against CAD and do dimensional inspection to check if everything is correct or as we intended it with the design. So this system can be used purely as a manual system. So you point the sensor, move the part, capture more data, and so on. It can be used in a semi-automated way. So that's where we would use a rotation table, automatic rotation table. You put the part on and you let the system do the rest. And we also have fully automated systems you see on the right-hand side. This is where we mount the sensor onto a robot. And in the picture you'll see here, this is a typical example of measuring multiple parts in one go. So in the medical world, say, for example, you want to measure multiple, it might be femorals, for example, or maybe bone screws, something like that. So you can measure multiple in one go, so it really speeds up your inspection. So I've got a short video that I'm just going to run through now, and it gives you a little flavor of how the system works in reality. So just a nice little video there to show an example of how the Atos side of things work. So it's capturing external data. So now we're going to jump into looking at a couple of examples of how this sort of technology is going to be used in the medical world. So there's a couple of pointers on here. I've actually taken this from another presentation, so there's a few things taken out of here that aren't really too relevant. But the information that I want to share here, it's a case that was done recently, and it fits quite nicely with the story that we try to tell with our systems. So we're very much providing a solution to a problem. So in this case, you have the surgeon who is fitting or implanting the knee to the patient, and before doing so, they do an MRI scan, and they would use that data to construct a surgical guide. And it's this guide that supports the femoral, the knee implant, in the right place, so that when they start to drill and fix it in position, it's actually in the correct place, and it's patient specific. So this is done individually every single time. So the key thing here is that the data that you take away from any scans needs to be as accurate and as repeatable as possible, because if the holes, for example, aren't in the right place, then the surgeon would need to close things up and return another day, which obviously isn't a good situation. So the little video that's going to run through here, it just shows a typical inspection process. So if I just play the video here. So you have the scan data. You can see there very high resolution scan data. You have the 3D printed guide underneath. And what we'll see in the next scan with the color plot there. So what I'll do is just pause it for a second, because what we're looking at here, this is typical inspection data that we're pulling out. So the resolution, the amount of data points that we capture as standard is very, very high. So you'll see here that if I just put my pointer on, you'll see you've got different colored areas here. So the blue areas are telling us where we don't have enough material. Red areas tell us where we have too much material, and green and those sort of warmer colors are telling us that maybe we're in the right place according to our tolerances. So what it starts to do is paint a picture of what is good and what is bad. So essentially the knee, the femoral itself, is going to sit into this guide. So the information that we can get from it is the knee going to sit correctly in the guide? In the case of this image here, you've got the diameter of the pins and the actual positions of the pins themselves, because it's highly important that is in the correct place. Again, as I say before, if it's not in the right place, then the surgery can't go ahead in this example. And so everything has to be repeated another day. So it's lost time, it's increased cost to the NHS, all things that are just really unacceptable. So a nice example of where this type of technology is used in a day-to-day basis. What I'm going to do now is just move on a little bit to the Aramis side that I talked about before. So just as a recap, Atos is for capturing external geometries, and we're digitizing and we're scanning the whole surface and creating a static digital twin of the part. What the Aramis systems are doing is it's optical, it's non-contact, but we're measuring deformation. We're looking at how things move, how things twist, and how they react to being put under load. So in a very similar way, we have a light. If I put on a mark here, we've got a light source, and then we have two very high-speed fast cameras, and these are able to give us very high frame rate measurements of the part, very high detail, and it gives us a lot of information, such as, again, how things move, not just in one axis, but how they move in 6 degrees of freedom in this case. So it can pretty much suit any application, but specifically today, we're just looking at medical. So the example we're going to look at here is the actual real-time motion analysis of the spine. So in particular, looking at, for example, there might be disc protrusions and that sort of information that we're trying to pull out. So in the video you see here, this is a sort of typical test rig, if you like. So they've taken a sort of section of spine, and you can see there's a number of dots that are positioned on it. This is what the system will use to be able to track in real time what is actually happening as the part is moving, or as the component is moving. And you can see here just a zoomed in section, in the sort of setup of this test, if you like, there are some pins that have been positioned into the actual bone itself, and they have little reference points on the top. Again, this just allows us to track what is going on. Again, the information that we gather from this, it allows us to create reference data, and then you can see from the different colors are representing different vertebrae in this example. And this is a nice slide here because it shows us how we can link Aramis data to different types of scan data. So in this case, it's CT scan. So we've got internal and external data going on. But once we have all that information together, I'll just feed on to the next one. This is now the sort of information that we can pull out of the using the software. So it's actually tracking those points and looking at the vectors. So as the part is put under load, what is actually happening. A simulation software may tell us that when you load it in a certain way, it will move in this way, it will twist, it will do whatever, and with a certain amount of force. So this data, because it's real time, it's actually looking at the part. This gives us real time information of how things move, at what force, and in what direction. So very, very powerful information. And this is just another example. So you can see the gray part. So these sections here, this is actual scan data. So this would have been captured with either Atos or maybe CT data. And we can then combine that with Aramis to actually see how things twist and how they move. Again, this is just the same sort of test, but looking at different data. So rotational movement graphically. So you can pick out certain points, as you can see on here. Again, if anybody's got any queries, any questions, pop it in the chat, and then we'll try to have a look at the end rather than sort of going through as we go along. Either put it in the chat or the Q&A. Again, a similar thing here. Once we've got the data, so if we've scanned it either with Atos or CT, once we've captured all that data, we've got a lot of options available to us of how we actually analyze that. And that's where it becomes very powerful, because traditional analysis of how things move might involve using strain gauges or LVDTs, that sort of thing. The problem you have there is that you're only measuring the strain or the stress in one particular place. You don't know what's happening elsewhere. And this is where this technology fits very well. So this is a nice slide here, because it's combining the two. It's combining scan data from Atos or CT, and it's looking at the actual gap between this particular vertebrae and the next one above it. So you can see from the color plot here that warmer colors are starting to indicate a larger gap, and sort of cooler colors are indicating a smaller gap. So it's very visual. You could show that to anyone and it's quite clear what's going on. So as the vertebrae are loaded, you can see that bigger gaps appear and obviously smaller gaps appear elsewhere. The next example I'd like to show you is again a leg artificial limb. So this is a similar sort of test, but we're looking at maybe a little bit of faster movement. So this is obviously slowed down slightly, but it's tracking the limb as the person's running on the treadmill. And the next slide, again, it just gives us real high level data to see, okay, how much is a particular, or how much is the blade moving in a certain area. And again, this is all to do with validating simulation data. Simulation data will tell us so much, but it's not real life. This is actually showing us what's happening in real time. And because we're actually tracking points on the part itself, we can actually use the software to pick out certain points and plot them graphically. So how is point 1 moving compared to point 2, point 3 in this case? So again, real powerful set of data. So that pretty much brings it to the end of the examples I wanted to show. There's another slide I want to show here, which is just for a little bit of fun, really. We engaged a lot of colleagues, both in the UK and worldwide, to share their own videos of using this type of data. And this is really just to show, you know, what you can do once you've got this data. It's not, you know, it's not specifically for looking at medical implants or for looking at how an airbag goes off and that sort of thing. So I'll just show this with you guys. So this, as I say, this was an actual competition we ran between all of our colleagues to see who could come up with the best idea, the best thing to track and to show. Hopefully this might be inspiring some of you as to where you could use a similar technology, or maybe it'll fit in for what you're doing as a work challenge. There we go. As I say, a bit of fun at the end, just to show you what's possible. So, summary of what we've talked about. So, the actual portfolio of solutions, if you like, is pretty much any solution to suit any budget and any application. We have systems that can be used to measure external geometries. So this would typically be the Atos systems. Or we can look at real-time deformation, displacement, stress, strain, and this would be the Aramis side of things. All of the systems can be scaled up or scaled down. So you have the sort of the main basis of the sensor, and then by just exchanging lenses, we can go from measuring something very small, so that the size of a coin, all the way up to something maybe as big as a wind turbine blade or a helicopter blade or a complete vehicle, a boat, anything like that. We have various solutions. They may come in the form of handheld systems, laser-based systems, manual or semi-automated systems, all the way through to fully automated solutions for measuring complete vehicles inside and out, as an example. One of the key things for us is that we have one software that suits all products. And this is a software that we've developed ourselves. It's very much a metrology-based software. So there are a lot of softwares out there that will do lots of different things. But in some cases, the actual metrology side, so pulling out dimensional information is sometimes not so slick, maybe a bit clunky. The software we've developed is very engineering driven, and as I say, you can use this software with multiple data sets. So you might have a point cloud data that's come from a CMM. You might have point cloud data that's come from a scanning arm, or just lots of single data points. This can all be pulled in and all analyzed using the GOM software. Whether you want to measure internal or external features, we have those solutions again within the Zeiss group, because we have CT systems now that can measure most materials, whether it's plastics, whether it's metals like steel, tungsten, cast iron, even something very, very dense. And the big plus point for CT or X-ray inspection is that you're not limited by the color of the material, the finish, whether you can physically see a particular point. It's not governed by line of sight. So CT inspection is very, very powerful, and we're starting to see that the CT is becoming more and more the sort of go-to inspection technology. And then lastly, probably the key point to take away, if anything else, is that the software is free. So if you just want it for evaluation of data, doing your own reports, playing around with data sets, that's all available completely free of charge. And then if you want to take that further and start to create trend data, run scripts to do fancy things, then that can move forward into a full-blown software package. But as I say, anything that you have any questions on, I can see there's a couple of questions in the Q&A. There's a few chat questions as well. Pop it in there. I've also put my details on there. So again, my name's Stuart Dix. I've also put the details down of a couple of my colleagues who are more involved in the testing side, the testing portfolio, than I would be. So if you have any questions at all, take a note of those guys' details, and we'll be happy to help. So I'm going to stop sharing, and we'll have a look at some questions. Thank you.
Thank you, Stuart. It was very excellent. I really enjoyed that. So it's a very informative talk. Well, obviously, there is no end to the number of applications of your software and hardwares, which includes GOM and perhaps like Carl Zeiss. Is it according to Carl?
Yes.
Carl Zeiss software. Yeah. It's a good. I think it's a good merger. It was beneficial for both companies. Let's see the questions. What we have here for Malcolm, are there any clinical data to show whether pre-operative 3D inspection of a cutting guide has any clinical significance in terms of patient outcomes?
It's a great question. And I've got a feeling that there's going to be lots of very good questions similar to that. What I would say is that certain questions that I can't answer, I'd love to be able to take them away, share them with colleagues, and see what we can come back with. So for that particular question, I would suggest you've got my details. So if you want to pop an email across, maybe with a bit more detail, expanding on what you've put there, and I can do my best to find the answer to that question. Because at the moment, I'm not sure what the right answer there is for that one. But please send it across, and we'll get you answered.
Okay, thank you. I hope, Malcolm, that satisfies your question. You're happy with that. Well, there is the other one, which is not a question. It's a request. Please do share these presentations. That's what anonymous attendee says or suggests. And there are some other guys in the chat box. Could you please forward me the slides PDF at the end? Sure, please send me, and so on. That's okay. Can you please put in? Yeah, okay. What website to download the software? That's a question.
Okay, so let me. What I will do is, if you just give me a second, I will copy the link, paste it into the chat box.
Great. Whilst you are doing that, as perhaps you all know, that this presentation has been recorded, is still being recorded, and it will be uploaded to the IET website, Facebook website, Facebook, which will be available within a few days, I believe, depending on Sandra's availability. I hope she can do that. And again, if you want to get the PDF files of Stuart's presentation, Stuart will send it to me, if not directly to you, but I can send it over to you. Please send me an email requesting the PDF files, the presentation. Okay, Stuart.
I've just popped in the chat the link.
I see.
It was to download the software. So if you follow that link, there'll be an option to download a free trial.
That's what they say. The free software, so you can play. Everybody can play with that free software. Is it?
Yeah.
That's GOM software. It's GOM your own. It's your own software.
Yes.
That's great. Now it looks like that we have no more formal questions, but let me just let me brave enough to ask some questions, Stuart. In terms of accuracy of the three-dimensional accuracy, how do you measure that, and what sort of accuracy can we talk about using your different devices and different softwares?
So all of the systems, whether it's Atos or Aramis or CT, they all are governed by accuracy data. So that there's certain values, like MPE values, for example, that talk about the measuring accuracy of a system. And depending on the system, they have a different artifact that we would use to verify the system capability and accuracy. So in the case of a fully automated system, that might be an ISO certified ball bar, for example, where we measure distance between the balls, and we verify that the distance between them is within set limits. The roundness of the balls is correct, etc.
When you say ball bars, it's similar to, is it the same than Renishaw as ball bars, is it?
Yeah, so the same sort of things as you would see with a CMM.
All right,
so you have a specified distance between them.
Yeah, the Renishaw has the same or similar device.
That's it, yeah. So we would use the same artifacts to basically just to verify that the systems are fit for purpose.
Yes. Well, people has got some courage now. John, what resolution can the matching work? What resolution can the matching work?
I'm not sure. Sorry, I'm not sure if I completely understand the question. The matching. What do you mean by that? Sorry.
Could it be the real life and your
I guess maybe
digital twin?
Yeah, I mean, what we would do is in the case of Atos, for example,
yes,
we have a mesh file which is hundreds of thousands of data points.
Sure.
And we would measure repeatably the same part and generate several meshes and then compare them against each other. So typically what we see is around about sort of anywhere from 5 to 10 microns of repeatability sort of data.
So that's matching. Well, John just clarified his question. He meant the surface matching accuracy.
Okay. So again, I guess that's related to, is that related more to Atos or maybe to Aramis? If I talk about the Atos side, when we measure the distance from a surface, we have to take into account that we're measuring point cloud data. So we may have data on top of data on top of data. So that's where the software comes in to thin that out. So we have just one continuous mesh that covers the surface. And again, we have aerospace customers who are probably our most stringent customers, because they force us to produce the best data, because as you can appreciate, nothing goes up in the sky unless it's been rigorously tested.
Sure. And
we generally compare, or what has happened in the past is we compare our data with sort of a high-end CMM, for example.
Right.
So coordinate measuring machines, your CMMs, have been used for many, many years as the go-to standard. So you might measure surface data points using the contact probe. So we've done data to match our full field data with the contact probe points. And typically what we see there is a repeatability of generally less than 10 microns.
Yeah, okay. I hope, John,
so hopefully that's answered the question.
If it's still unclear, please, John, contact Stuart by an email or somehow. Well, another question from John. What does MPE stand for, please?
So MPE is just the measuring accuracy of a system. So you might have several sort of suffixes to that. So you have MPE that may be looking at linear accuracy. You might have MPE that looks at volumetric accuracy.
Right.
So MPE is just talking about the accuracy of a system, the calibrated accuracy.
Right. I hope it does the job. Again, from John, does sensitivity vary depending on the surface properties?
So yeah, another good question, and the quick answer there is yes. So you may have a surface of a component which is maybe it's been shot blasted, so it's fairly rough. You may have a surface that's completely polished, and depending on the system, so Atos and Aramis, they're non-contacts. They use optical technologies, so there can be some. You can have reflections due to the surface, and that can cause extra noise in the data, which can give you some challenges. So this is where things like CT data becomes very, very powerful, because it's less affected by the actual surface condition of the part. Right. But very good question.
So it's not only the surface accuracy in terms of RA value, RT value. It's about how it shines. It's a shiny surface. It absorbs the light.
It can be, it can be that as well, Andrew. Yeah, if you've got a component that actually does absorb the light as it hits it, then that can also give challenges. But there are certain products on the market, digitizing sprays they're called, that you apply a light dusting onto the part, and what that does is it limits reflections.
Right. Okay.
The technology moves along quite fast, so we're seeing now that there's less occasions where we need that.
Thank you, John, for your questions. I hope he satisfies, and thanks for the answers, Stuart. Well, we talked about, you mentioned, we focused on biomedical engineering, various parts going into the human body and so on. In terms of application areas, what other areas do you tackle?
Sorry, can you just repeat that, Andrew? I was actually just reading a question that was going to be.
Okay. Let's go to the questions now. Dr. John again. Well, it's a question mark. John again, 70 nanometers apparently. That's what he says. And again, he says, thank you.
So I think what John's referring to there is he's referred to a specific system, the Zeiss X Radio, which is a CT system.
Yeah. Okay.
And he mentions there 70 nanometers voxel. So a voxel is basically just a three-dimensional pixel. And that's what's used in the CT world. And again, it depends on the system. As a general rule of thumb for CT, the smaller the component is, the higher the resolution, the higher accuracy we can get, because we're closer to the source.
Yeah. Okay, I think it's John is okay now. Then Malcolm, in healthcare, biomechanics, rehabilitation, engineering departments, the Vicon biomechanics system is very common. It's a statement. The question is, could you explain how your system differs from something like that?
Yeah, a good question. And the quick answer there is I can't explain. That would really be a question for Amy or Rob, who spend all of their time dealing with the testing systems. So they would know of all of the different systems out there. But,
which means if Malcolm contacts you with this question, you can pass it to Amy.
Yeah, I mean, maybe Malcolm's got a specific query related to these Vicon systems. I'm not sure, but if there is something specific that you'd like to learn, then
right, okay.
Please pop an email across, and we can we can try and help you.
Right. So my questions, which wasn't quite clear, was about the application areas. We focused on biomedical engineering, and you mentioned, was it turbine blades? And perhaps you mentioned aerospace engineering as well. What other areas, industries or applications do you have for other industries?
So there's no limit really.
No limit, yeah.
Andrew. Yeah, I mean, you have aerospace, automotive are probably the strongest, closely followed by medical. But you have nuclear applications. You have sort of industry applications. So that might be anything. You know, it could be 3D printed or plastic injection molded parts for washing machines.
So there's no end to it, is it? There is no end to it. It's just any applications, really. Yeah. It's almost any applications.
I suppose the quickest way to answer that really is if you can physically make something, then there is a need then to be able to inspect it.
Right. Okay. I think it answers Malcolm's question as well. Okay. Well, I think that's the conclusion. We have to conclude now. And well, it's been very nice, very comprehensive presentation on many areas, and including various devices and application areas, but mostly focused on medical engineering, biomedical engineering, which was really great. I'm pretty sure that the audience enjoyed that, just as I enjoyed that. So I'd like to say thank you very much, Stuart, for providing this presentation, and please send the PDF files of your presentation to me in due course, and I will forward them to the people who requested that. Another thank you goes to the IT staff, Sandra Lucy, who managed to organize this meeting on behalf of the IET. And the final thank you goes to the audience, who kindly gave up their time and joined us today to view this webinar. And it was really great. And I believe that, well, you audience, you come again to our forthcoming webinars, as I just discussed and presented it to you. Thank you, everybody. And thank you for the presentation, and have a safe journey home. You are at home, I'm sure. I just say have a safe journey home. If it was a normal time, it's still not normal time. We try to come back to normality from September. It looks like no more questions. Thank you again, Stuart. Give my regards to the staff at Com Zeiss at your place.
Oh dear,
thank you so much. And again, see you soon. We have to talk about other things as well. Thank you.
Thank you, everyone.
Thank you. Bye-bye now.
Cheers.
Bye.